Hi, I'm Darren Decker and this is Herb Brooks, and we're going to demonstrate how to install a capillary GC column. This demonstration is suitable for the majority of capillary columns that Agilent manufactures. There may be more specific conditioning, care, and maintenance procedures for your new GC column. Be certain to read all the information that comes with your column. There are a few tools you'll need to change your column. You'll want a column cutting tool. A ceramic wafer, which is shown here, is pretty much the standard these days. We used to use a sapphire rod or a diamond tip scribe back in the day, but ever since the ceramic wafer has been around, it pretty much retired the other cutters because it's so easy to use. A magnifying glass is good to have on hand to inspect your column cuts. You also might want to have a supply of an appropriate non-retained compound such as methane or butane if you're using an FID. For a mass spec, you can use argon or air. It's a good idea to have an electronic flow meter and an electric leak detector on hand too. Finally, you might want to have a test mix ready to run when you're done installing your column. But this is not necessary because every Agilent column is pre-tested before it is sent to you. So you have a high level of confidence that it will work as expected right out of the box. I'd like to have one of my standards around to inject to verify that everything's installed correctly and the settings are right. Nothing tells me my system's ready like my standard. Of course, you'll want to wear safety glasses, and a lot of people like to use gloves when handling columns. There actually is a bit of debate over whether or not to use gloves. I guess as far as I'm concerned, I just want to make sure that you don't get anything on the part of the column that will be in the flow path and then show up in your system. Any contamination, especially oily things, can be pretty persistent if it gets in the flow path. You don't want to chromatograph your lunch. Here's what a French fry looks like. Check out the experiment. They held a French fry for 5 seconds, then wiped their finger to remove as much of the offending material as possible, then lightly touched the part of the column above the ferrule, installed it, and voila, French fry. Now, this will go away over time, but better off to start without it. Does that mean we need gloves? No, it just means make sure your hands are clean before installing a column. But even that can be troublesome. Here's what liquid soap looks like with the same experiment. Remember, a little goes a long way. Now, in my opinion, gloves are not necessary, and if you have problems like this, just make sure you take a lab wipe, put some acetone or methanol on it, and just wipe off the ends of the column before you install them. If you never see this, don't worry about it. Now, before we get started, it's a good time to check gas traps for expiration and replace if necessary. We're on the new system, our traps are fine. Since the system is down for a column change, it's a good time to change any inlet consumables as well. Install a new septa in the inlet, look at your liner. If it's visibly dirty, you should replace it. Sometimes, even though it looks clean, the liner needs to be replaced because it becomes active. This is usually seen on the chromatographic results as a loss in response or tailing of active compounds. If for any reason the liner needs to be replaced, make sure to use new O-rings. O-rings break down and lose their elasticity over time, and you usually don't get as good of a seal if you try to reuse it. If the liner is dirty or damaged, chances are the stationary phase on the first portion of the column is as well. Also, the liquid phase in the column can be easily damaged by oxygen at temperatures above ambient, so making sure everything is leak-free after we're done is critical. Agilent also recommends using traps on the carrier gas lines as an extra measure of protection against contaminants, and therefore, it'll extend your column lifetime and minimize background noise. Our gas management video covers more information about that. We do need to be careful when cutting columns as they are made of glass, so safety glasses are a must. So let's get started. First, we place the column on the GC oven column hanger, making sure that the column tubing does not touch any of the sides of the oven. Now we need to unwind enough column to obtain a smoothly curved section of tubing connected to the inlet. Avoid tight bends as this stresses the tubing and could cause breakage. Make sure that the column tags, sharp edges, or other items don't rub against the column. Next, we place the column nut and ferrule over one end of the column. Now, we like to put a septa on there first because we're going to use that to help us in the measurement later. Now, there is no front or back to the column. However, most people I know install the column with the post of the column cage pointing towards the oven door. We cut the end of the column after nut and ferrule placement so that we don't leave any ferrule material in the end of the column. Hold a section of the column like this. If you run your finger on the edges of the ceramic wafer, you'll notice there's a rough and a smooth edge. You want to use the smooth edge towards the column. In one motion, run the edge of the ceramic wafer at a slight angle across the edge of the column. Do not press hard enough to cut completely through the tubing, but hard enough to cut the outside polyimide coating and score the underlying glass. Grasp the column on each side of the scribe mark, bend it away from the mark, or sometimes I just like to hit the top of it with the wafer, and then pull it away after it breaks. Inspect the column end with a magnifier. Ensure the cut is at a right angle to the tubing wall, free of any chips, burrs, excess polyimide hanging out, or any uneven areas. And do it again if necessary. Now, the optimal insertion distance for most installations of the column into the splitless inlet is going to be 4 to 6 millimeters from the top of the ferrule to the tip of the column, but this might change for certain liners. Call technical support if you have any questions on the proper length. We want to make sure the tip of the column is just above the gold seal. Now, a little bit high is okay, but too low will be a problem. After setting the distance, this would be a good time to wipe the end of the column with a lab wipe and some acetone or methanol, like we talked about earlier. For other inlets, other than the splitless, consult the GC instruction manual for the proper insertion depth and technique. Now, with the column at its proper position, finger tighten the column nut, using a wrench to tighten an additional half turn. If the column can be moved in the fitting, tighten another quarter turn. Failure to achieve a leak-free seal will cause rapid and permanent column damage when you heat the column. Do not move the column while tightening the nut. Now, people have used liquid paper in the past to mark the column at the proper distance, but as I said earlier, we like using a septa already on the column to hold it in position. So before you even put the nut and ferrule on, make sure you put that old septa on, and it's a nice little trick. Ferrules, especially those made of graphite Vespel, will change shape slightly upon heating. If the column was installed while the inlet and detector were cool, retighten the fitting. It's also good practice to check again after conditioning of the column just to make sure that the column nuts are tight. Adjust the head pressure to obtain a reasonable gas flow rate. The setting will vary. For example, for a 30-meter column using helium carrier gas, the head pressure setting is going to be between 15 and 25 psi for a 0.25 millimeter ID column. These values are recommended starting points only. The actual head pressure will depend on the carrier flow rate that you need in your method. Next, we'll place the free end of the column in a small vial of hexane or water or some suitable solvent. And what we're looking for is a steady stream of bubbles. If the bubbles aren't seen, we need to check the carrier gas supply, flow controllers, etc. for proper settings and for leaks. As long as we've got those bubbles, we're fine. Now we'll wipe off any residual solvent using our lab wipe. For our carrier gas, we want to use high purity hydrogen or helium. Nitrogen was once popular, but for most applications, it's not recommended anymore. Whatever carrier gas you use, a purity of 99.995% or better is recommended. Again, the most important impurity is oxygen, and it must be avoided. You want less than 1 ppm of oxygen in your gas, or you'll damage your column when it gets hot. Now we're ready to install the column into the detector. And we'll follow the same process just as we did for the inlet. We've already got our septa, our nut, and our ferrule on. We've made a clean cut, and we're just going to put it in there, get it nice and snug. We should also inspect for leaks. We can use an electronic leak detector to do this. We'll look at both fittings, both the inlet and the detector. Electronic pressure control allows direct entry of carrier gas linear velocity or flow rate. It's critical that the correct column dimensions are entered into the PC software or via the GC keypad for accurate velocity or flow values to be set. Always consult the column performance summary sheet that accompanies the column for accurate inner diameter information. This is when the test mix or one of your standard comes in handy to verify the settings. We should have something of known retention in the mix to make sure that all our settings are correct. And of course, we're looking for good peak shapes to confirm good installation. We can also verify carrier gas velocity by injecting a non-retained compound. We'll start with our oven at about 35 to 40 degrees Celsius. Now we're going to inject 1 to 2 microliters of a non-retained compound with the split-splitless inlet mode in the split mode. Now if you're using Megabore Direct or Cool-on Column or even splitless, dilute the non-retained compound a little bit so the sample won't saturate the detector. Now most people use methane here, but a good trick that you see people use all over the place is they use a butane lighter. It's easily accessible and all we need is a little bit of gas. Make sure you don't light the lighter, but pull up a microliter or 2 of that gas and then just rapidly inject it, start the GC, and look for a very sharp symmetrical peak. Now a small amount of peak tailing might be observed with splitless injection. If no peak appears, there may not be any carrier gas flow. Check the regulators, the gas supply, flow controllers for the proper settings, and make sure that the detector, the recorder, the syringe are all functioning properly. If the non-retained compound is tailing, there may be a leak in the inlet, or we may have poor column installation, or an excessively low split ratio. Reinstall the column, check the settings, and check the inlet for leaks. A non-tailing peak is required before we continue. Now, let's condition the column. Heating a column without flow or while oxygen is present in the carrier gas stream will ruin the column. First, make sure that all the oxygen's been purged from your column. Letting the column purge with carrier gas for 15 minutes is usually sufficient. Heat the column to its upper temperature limit or a temperature 10 to 20 degrees above the highest operating temperature of the method, whichever's lower. Don't exceed the column upper limit or column damage will result. The rate of heating is not critical, but being oxygen and leak-free is. Observe the baseline as you do the conditioning procedure. You may see some artifacts, peaks, from the installation process, but they shouldn't be persistent. After the column has reached the conditioning temperature, observe the baseline. If it continues to rise as you hold temperature, you may want to check for leaks. If it rises, then falls, you may have just eluted some higher molecular weight contamination that was transferred to the column as you installed it. A flat baseline is what you're after. You should be able to get that in a reasonable time, depending on the state of the instrument when the column was installed. You could be ready in as little as 15 minutes, or it could take more than an hour after reaching the conditioning temperature. If the baseline doesn't stable after 2 or 3 hours and does not remain constant, stop the conditioning process. An unstable baseline can be caused by a leak in the carrier line or inlet area or by system contamination. You're probably better off to cool it down and fix the problem before continuing. Polar stationary phases and thick films usually require longer times to stabilize than non-polar phases and thinner films. Plot columns, porous layer open tubular columns, require special conditioning procedures. Refer to the column information sheet for the appropriate procedure. Now when it comes to ECDs and MSDs, some believe these detectors may stabilize faster if the column's not connected to the detector during column conditioning. The problem with doing that is you won't know if you do have an unstable baseline or a leak, and if you condition the column with a leak, you'll cause irreparable damage to the column, giving it a high bleed or making it active. If the column is conditioned with the detector and disconnected, I'd recommend you remove a small portion of the column end as it may be damaged. Remove 10 to 20 centimeters of the exposed column end before connecting the column to the detector. For capillary columns, the average linear velocity is a better and more meaningful measure of the carrier gas than volumetric flow rate. Velocity just talks about the speed of the gas, and so we don't need to know the volume of the column or what diameter we're using. Since the gas viscosity changes with temperature, you need different pressures at different temperatures to obtain the same carrier gas average linear velocity. Therefore, always set the carrier gas average linear velocity at the same temperature for a given analysis, and often this is the initial oven temperature. Now, if you want, you can inject 1 to 2 microliters of the appropriate non-retained compound and calculate the linear velocity, as we showed, using the retention time of that peak in the equation that we're showing now. Adjust the column head pressure until the desired average velocity is obtained. For GCs with EPC, the linear velocity can be entered into the PC or the GC keypad. The correct dimensions must be entered, as we stated earlier. Refer to the dimensions listed on the column performance summary sheet, as we mentioned earlier, to get the most accurate information. Now, length can be estimated by counting the loops on the column cage and multiplying by 0.54 meters for a standard cage or 0.4 meters for a 5-inch cage. Contact Agilent technical support for additional information. It's always a good idea to see what your system looks like with no sample or a blank run. This can be valuable for troubleshooting later if a problem arises. After the column is conditioned, go ahead and run a blank run. You can use your standard temperature program or the following. Start at 40 to 50, ramp 10 to 20 degrees per minute up to whatever your high temperature is, 300 degrees, and hold at that temperature for 10 to 15 minutes. Save this background trace for future comparisons. It could come in handy for troubleshooting, as I said earlier. There should be no peaks in the blank chromatogram. Peaks indicate a contamination problem prior to the column, usually in the inlet area or even before that. As a column degrades with normal usage, the magnitude of the baseline rise will increase. If a baseline rise occurs at a much lower temperature than previously obtained, the column and/or the GC is most likely contaminated or perhaps damaged. Well, now you're ready to begin operating as usual.